Okay. Hello, everyone. Thanks for coming. It's very good for you to give your time to watch this paper reading group. And hello, guys, for the YouTube audience. You are so awesome. You are so good for giving your time to watch this video. Thank you for giving the time. So now I will talk about the cohort state transition model. So this paper was originally written by the Dart group. So I'm standing here as a representation of the Dart group. And for the preliminary, you don't have to do any much stuff about programming. Maybe a basic R will help. And basic economic background will be very helpful because there are some economic terms that I will discuss in this presentation. So a little bit about my background. Currently, I'm doing statistics specialist in data science and machine learning stream, majoring in computer science, and also minoring in economics. And now we can do something about the Dart group here. So the Dart group is actually a combination of scientists from people around the world. There are people from the Sick Kids Hospital, from Stanford University, from University of Ottawa. There are people from Netherlands as well, from the Erasmus Medical Center. And good trivia for you guys to begin with is, what is Dart actually? Anyone want to answer? What is Dart? Yeah, sure, you.
Is it option A?
Yeah, correct. I will throw you candy here. Nice catch. So Malhar is correct. So Dart is actually an abbreviation of decision analysis in R for technologies in health. So they make a team to collaborate for open source library in R especially, and it is used for the health decision analysis. Okay, and now let's begin with the paper introduction. So imagine you are a policymaker. So I know most of you guys are software engineering or future statistician, but for example, you are making a decision for assigning people or creating a policy for a company in terms of health. So you have a budget and you want to decide which policy that you want to use to cure the disease for the patients, for the clients that your company is dealing with. So of course, you don't just make the decision right away. You need some framework, or it's called decision model, to decide what is the best health decision for your company. And one of the most famous decision model is the cohort state transition model, which we sometimes call the Markov model. And also, actually, I know you guys are programming, so you know there are a lot of libraries out there in Python, in Julia, in C++, and even in R. Two of them are very famous, which is the he mode and also the Markov chain. So for cSTM, Markov chain is very good for the time-independent model, but they are not designed for the economic evaluation. But on the other hand, he mode is good for economic evaluation. But the problems are those two are very stylized and very structured, like to design cSTM. But the problem is this word is growing, and people are growing, and they are predicted to be like 10 millions in around 20 something, and it's like it means like the problems are growing, and it might be not as stylized and as structured based on the package. So we, like Dart group, created this paper for you guys to design the cSTM by yourself. So it will help designing cSTM independent without any specialized package. So, okay guys, so we have those graph with a bunch of circles and a bunch of arrows. So anyone can guess what does those circles represent, and what does those arrows represent? Anyone? Sure.
The health state of a patient.
Yes, exactly. Thank you for being very active. So this is the diagram of the cohort state transition model, and as that very genius student said, those circles and arrows represent the health state and transition probabilities. There are very important 6 characteristics of cSTM. The first one is we assume that those health states are mutually exclusive but also exhaustive. And we are assuming all individuals in the cohort to be homogeneous, so they are indistinguishable. And those arrows, like, we want to define the probabilities of those individuals in that cohort. Either they want to move or they want to stay in that same state. We define that as the transition probabilities. And the transition probabilities, we are assuming that they are time independent. So it means we cannot include the history of the patients. For example, like you have diabetes, and your parents, for example, have the diabetes history. So, like in terms of medical, of course, because you have like diabetes history, then it would be higher. You have the higher risk to get diabetes than other people who don't have like diabetes history. So you cannot include the history for the patient. That's one of the like minus from the cohort state transition model. And we all also assuming that the rate of becoming sick is constant over years. So what does that mean? For example, so we are starting from people with 25 years old up to 100 years old if they are still alive. So of course, like as you are older, the rate of becoming sick is higher. But in this model, because they are time independent, we are assuming that the rate of becoming sick is constant. Like that's another minus for the cohort state transition model, which we actually already handled those 2 minus in the like next paper, which is called the approximate bias computation. So we will talk about those later, maybe like if we have time. I mean, I just stated that facts so that you are interested to read our other papers. And we want to define what is the meaning of rate versus probabilities in this paper, because it's different with like some people who already learned this definition. So, So suppose there are 10,000 person years of observation, and we observe there are 500 events of interest, which in this case is becoming sick from a disease. So anyone can guess what is the rate and what is the probability? Sure.
The probability is 5%?
So that's what we need to define it in the beginning, because the definition of rate and probabilities in this paper is very different. So in this paper, rate is defined as the number of event, I think it's okay. So in this paper, rate is defined as the number of event over the sample. So in this case, it is 500 over 10,000, which is 0.05, which is or 5%. And then in this paper, probability is defined using the CDF of the exponential distribution, which is 1 minus exponential of minus rate, which is in this case 0.05, which is around 0.048. So this is what makes those definitions are different with what we've learned so far in university. And how about months? If we want to do months, because like in this paper we are assuming this is like yearly cycle. So for month, we want to divide this rate by 12. So we just divide this by 12. So this is just this one. But we cannot just divide this over 12, but by definition of the CDF of exponential distribution. That's why we need to define the probability for month is 1 minus exp of minus 0.05 over 12. That's how we define the rate and probability in this paper. Everything looks so fine, guys, or do you have any questions? For you guys, if you have any questions for the YouTube audience, you can just put it in the comment and we will answer it for you guys. And now we are discussing about the components of this model. So there are three very important components in this model. The first one is the state factor, which is just actually your health states. We have, in this case, is health. So this is a factor. So like in R, we represent it by C. So it has healthy state. It has S1 state, which I will explain it later. And we have seeker state and the dead state. So that's for MT. And for the And also, in this case, MT means the state vector at cycle t. So this is for cycle t. We have number of cycle is equal to nt, which I will define later. And we also have the capital M here, which is just actually a bunch of the vector, and we stuck it from the cycle 0, cycle 1, up to stack of number of cycles. And finally, we have the transition probability matrix, which is defined as the matrix from of the P of ij. So here, P of ij represents the probabilities of moving from state I to state j. So for example, if you have the probability of 1, 2, so it means the probability of transitioning from state 1 to state 2. So you have this one is equal to P 1, 1. And so we have the rows here is equal to number of state here. Sorry, the rows is the number of cycles, and the columns is the number of states. And because we start from cycle 0, like in our code, it will be nt plus 1 because we start from cycle 0. And this is how we define those variables in R. Sorry.
I have a question. So the probability matrix, wouldn't it just be number of states by number of states? Because that's how you're defining Pij, right?
Yeah, thank you. That's correct. Yeah, thank you. My bad. Yeah, this is actually number of states times number of states. Sorry. Yeah, that's for the M. Sorry. So, like if we expand the n, like the dimension of M, the row is here we have, this is like M0, M1 until MNT. So the rows is actually number of cycle plus 1 because we start from cycle 0, cycle 1, up to cycle nt. And the number of columns is basically by definition of M, by definition of the vector mt, it is equal to the number of states. Sorry. So the rows for, so the dimension of M is the number of cycle plus 1 and the number of states. Sorry for the confusion, guys. So, and actually, there are some rules that we need to define by definition of probability, which is so for each probability, the sum is equal to 1 for each row. For each row I. So that's something that we need to check. So we will use the row sum function in R to check this. So, and also of course the probability is between 0 and 1. So we need to check this for every cycle to make sure that what we have done is correct. And this is like the components, how we define those in R, which is, I will explain the naming convention in the next slide. Sorry.
Would the probability ever be equal to 0 or equal to 1?
Yeah, that's true. Sometimes it's equal to 0, sometimes it's equal to 1. Thank you. And for the naming convention, so by the convention from the Dart group, the first letter represents the data type. It can be no prefix for scalar, V for vector, DF for data frame, and M for matrix. And the second letter represents the variable type, so P for the probability, R for rate, HR for hazard ratio, C for cost, and U for utility, or in this case, utility represents quality of life. So maybe like some background for the utility. The utility represents like is equal to 1 if you are healthy, and it's equal to 0 if it is dead. So it represents your quality of life. And if you, for example, have phi underscore p underscore hd, what does it represent? Anyone can answer? Sure, you, Anaki.
V would be vector,
Mm-hmm.
P would be probability,
Sure.
and HD is from healthy to death.
Exactly. Wait. So this is the candy for you, Anaki. That's very good. I hope you guys, the YouTube audience, can understand it as well. If you have any questions, you can just drop it in the comments and we will answer it for you. And maybe like a little briefly explanation about this description of parameters of their R variable name, or their base case values and distribution. So this is like very important. So we are like what I've mentioned it before. So we start from people with 25 years old, ending until 100 years old. So we have 75 cycles, just 100 minus 25. And the health states, I've already said before. And also, we assume the discount rate, which is just the synonym for inflation. We are assuming we have 10% inflation rate. And the number of individuals, let's say, in the cohort is 1,000. And the rate, so like as you've seen here, like in this cohort state transition model, we have some arrows which we cannot like just know the value. So of course we need to define some initial values for some probabilities, some transition probabilities, so that we can define other probabilities. And in this case, we want to define first the probability for from healthy to sick. So we define the rate, which is 0.15. So this is like 1 minus e to the minus 0.5 here. And we also define from S1 to health, so it is equal to 1 minus e to 0.5. And we also define for sick to sicker here, which is 1 minus e to 0.105. Don't forget the minus. And we are assuming that those rates follow the gamma distribution. And we are also assuming this from healthy to death. They are following the gamma distribution as well. So that's equal to 1 minus E minus 0.002. So the background mortality rate, we are assuming they are 0.2%. And we have the cost. If you are healthy, then you need to pay $2,000 for a year to stay healthy, 4,000 if you become sick, 15,000 if you are sicker, and if you are dead, of course, you don't have to pay anything again. And for the quality of life, we are assuming if you are sick, the quality of life becomes 0.75. You are sicker, then your quality of life is 0.5. And for the treatment, we will define the strategies later. So the strategies we are defining, there are 4 strategies. The first one is strategy A, which increase the utility or quality of life. If you are sick, it becomes from 0.75 to 0.95, and it costs you $12,000 per year. And for treatment B, it reduces the rate from, so it will reduce this 0.105 by 40%. So it's just minus 0.105 times 0.6. If you have treatment B, and it will cost you $13,000. And the strategy AB, which is combination of both, so you increase the quality of life and also you reduce the rate of becoming sicker. And now we will just defining those values in R. And maybe I missed the part where I do not explain about the hazard ratio. So the hazard ratio, if, for example, you have the initial initial rate, if you are healthy, then there is 0.2% chance that you are suddenly dead. But if you are sick, then it becomes not 1 minus 0.02002 again. It will become 3 times higher. So it will become 1 minus E minus 0.02 times 3. So it is the definition of the hazard ratio. And if you are sicker, then it becomes 1 minus E minus the original mortality date, 0.002, times the hazard ratio, which is times 10 here. So that's the definition of the hazard ratio. And we want to compute that by using the CDF of the CDF of exponential distribution. And here's like if you are using strategy B, then you multiply that by 0.6 as I've already written here. And for the cost, I've already mentioned it before, which is 2,000, 4,000, 15,000, and the cost for treatment is 12,000, and the cost for treatment B is 13,000. Okay, let's make this becomes more interactive. Assuming that you are healthy, then what kind of cost that you're gonna pay when you are healthy? Anyone can give examples like bills that you're gonna pay if you are healthy? Sure, both of you.
Regular checkup,
Exactly. And you, Anarchy?
gym membership.
Sure, that's true. So Both of you guys can get candy. Sure. So that's why we do not assume if you are healthy, then you do not pay any bills for your health care, because there are any health care besides when if you are just paying for your drugs, then you don't pay, you can pay anything besides drugs if you are healthy. So, and utilities, which is quality of life. Maybe I will emphasize it again. If you are receiving treatment A, then you improve your quality of life from 7.5 to 9.5. And we have already discussed about the hazard ratio here, and also we've already discussed about like when you are using treatment B, then you have special treatment, special variable if you are doing the treatment B, which is you multiply the rate by 0.6. We want to initialize the factor, which is, so in this model, we are assuming that all of those 1,000 individuals to become healthy. So we have the probability is 1 for healthy, and the others are 0. And we initialize the big matrix M here, the big matrix of M, which has rows the number of cycles plus 1, and columns is equal to number of states here. And for each cycle, so to access, so again, maybe like you are CS kids, so you are very familiar with Java, Python, and C or C++. They start with index 0, but in R, we start with index 1. That's why we need to like insert the initial factor to index 1 instead of index 0. This is something new if you are new to R. So you insert the initial factor here to index 1, index 2, until index nt plus 1. And we also initialize the transition probability matrix, which has dimension number of states times number of states. And this is something that I want to explain it very clearly. Oh. Okay, so if you want to access the transition probabilities from state I to state j, then you enter the index, which is the name of the state. So H for healthy, S1 for sick, S2 for sicker, D for dead. So why we define the probability of healthy to healthy is 1 minus P underscore HD times 1 minus P underscore H S1. So here we have probability of healthy is this arrow. So first, we have to always assume that those arrows are conditional probability, because if they are healthy, it means they are not dead. That's why we use 1 minus P underscore HD, because this is conditionally if they are alive. That's why we multiply by 1 minus P underscore HD, because this is conditional probability. And also this is like from healthy to healthy. So it is another conditional probability. So you are assuming that they are not sick. That's why. Because from healthy, you can become dead or you can become sick. That's why you need to multiply by 1 minus p underscore hs1, because again, this is conditional probability. And the special case, if you are dead, then you just use the background mortality rate, which we've already defined in the previous code. So because the dead state is absorbing, it means if you are dead, then you cannot go to any other state. That's why we just define it p underscore the name state dead. So that's why we just define it like that. And if you are dead, then the probability that you becomes dead is 1, because again, because they are absorbing state. For the strategy A, you just copy it from the original matrix, but for strategy B, because you will reduce the rate of becoming sicker by 40%, you need to take into account the time 0.6. That's why you add by the probability of becoming sicker from sick state for treatment B. And for the strategy AB, because A doesn't do anything, so the AB just depends on the strategy B. And as I've mentioned it earlier, you want to check the probabilities in between 0 and 1, and we want to check that the sum for probabilities for each row it is equal to 1. And this is very important. So for each cycle mt plus 1, for the next factor for the next cycle, we get the value by multiplying the previous halt state multiplied by the transition probabilities. So mt stands for the halt state at cycle t multiplied by the big P, which is the transition probability matrix. And in R, in order to do matrix multiplication, we use percent star percent. So that's how we do matrix multiplication in R. And if you look at this equation, like the dimension is always the same, because this is like from 1 minus ns, and this is 1 ns times ns. So we get like the column here is correct, and the result is always 1 times ns. So this equation is correct because their dimensions are matched, and the result that we get is also the same. So our equation is valid, and we get the distribution of cohort. So this is the result when you do this matrix multiplication for 6 times. So first we have all of them in the healthy state, so the probabilities are 1. But as you've seen here, as the cycle goes on, because the dead state is an absorbing state, that's why if you see the graph here, the D graph, they are always increasing because they are absorbing. So if you are dead, then you are staying in that state. That's why they are increasing as the time goes on. And it actually makes sense. The model makes sense, very makes sense, because you know, as people grows older, then the probability of their death is higher and higher. That's why the distribution of dead people will be higher. And we want to define state rewards. So state rewards refers to a value assigned to the outcome of interest. So we want to know how about the cost. So we from the previous slide, we know about the distribution of people becomes healthy, people become sick, how much proportion of people become sicker, and proportion of people becomes dead. But how about the cost? How about the utility or quality of life? How we can compute those values for the state rewards? That's why we will use equation y is equal to mr. So anyone can guess what is the dimension of matrix M and what is the dimension of R? So yeah, you. Yeah, exactly. That's correct. So thank you for answering the question. So you are correct. The dimension of matrix M is just basically just nt plus 1 of, so here, like why we are, like why those things are very important, because again, in the matrix multiplication, dimension is very important, because if the dimensions are not matched, then the multiplication is not valid. That's why we always need to know the dimensions of those matrix multiplications. So we have the dimension for M is nt plus 1. So the number of cycles plus 1 times number of states. And R is actually the outcome of interest. So R, in this case, can be utility if you want to compute the quality of life. And it can be the cost if you want to compute the cost. So in here, Y represents the expected outcome of interest for cycle T. So we will have nt plus 1 Y, because this is expected outcome of interest at cycle T. So for example, in cycle T, we have this Y. So Y will have nt plus 1 times 1. So this is the factor of outcome of interest for each cycle. So expected outcome of interest for cycle 0 is y0, y1 until nt plus 1. So this is the expected cost at cycle 1, expected cost at cycle 2, and etc. And R is basically just the factor with dimension ns times 1. So to be precise, R is actually the factor of state rewards or factor of outcome of interest with dimension ns plus 1, ns times 1 here. And this is how we can, so we want to build the factor of quality of life. So this is for the standard of care. So this is like very standard, because we do not give any specialization for the standard of care. So we have for healthy state, we have cost for healthy state, but for the utility we have it is equal to utility for each state and cost for each state, and times cycle length. Cycle length in this case is just 1, because we are assuming yearly model. So this is just cycle underscore length, which is just 1, so we can just ignore it. And for strategy A, this is important. Recall that strategy A, we are increasing the utility from 0.75 to 0.95. That's why we need special treatment for treatment A. And for treatment B, it's just the same thing with the standard of care. And for the strategy AB, because there are combination of strategy A and strategy B, that's why we need to just copy this from the strategy A. And for the cost, we need to include for, so if you are doing strategy A, then you need to add by the cost for treatment A. Like if you are going back to the standard of care, they are just C underscore H, C underscore S1, C underscore S2, and etc. But if you are doing some treatment, then you of course need to add the cost for each treatment. And for treatment AB, which is the most expensive treatment, you need to add both costs. And now we want to compute the quality of life and also the cost. So QALY, it means quality adjusted life years, or we can just call the quality of life. So we use this equation, y is equal to m times r here. So the matrix for each strategy times multiply by the factor of outcome of interest. So for example, if you want to compute the quality of life, you multiply by the factor of utility. If you want to compute the cost, then you multiply by the factor of cost. And you need to do that for all those 4 strategies. And we are doing the discrete model because, like, if we see the way we are defining the matrix, the way we are defining the factor, we are assuming that they are discrete, not continuous. So we need to correct some values for the matrix and also for the factor. That's why we need to do within cycle correction. In this case, we are using the 1/3 Simpson rules to reduce the bias, because we are assuming, of course, you cannot jump for age 25 to suddenly you are become 26. Of course, you have 25 years old and 1 month, 25 years old and 2 months, 25 years old and 5 months, and etc. Of course, you cannot just assume that you are become suddenly from 25 to 26. And even if you are using the monthly model, then, for example, you are 18 months years old. You cannot just suddenly become 19 years old. Of course, you will pass the value of 18.1, 18.2 months. So that's why we need to multiply by the within cycle correction to prevent any bias, because we are assuming the continuous model. So for the Simpson rule, is basically you multiply by 1/3 for the first and the last index. So the first index, like I said before, in R you start with 1, and the last index is the number of cycles plus 1. And if for the even entries, you multiply by 2/3, and if it is odd, you multiply by 4/3. And we also want to take into account the inflation. So the way we are doing, taking into account the inflation, is we multiply by 1 plus d. For example, so $50 in year 1950, it will become very different, the value of $50 in year 2000. That's why we need to take into account the net present value. So how we are calculating this is just 50 times 1 plus d in cycle 0, and the next cycle we multiply by 1 plus d over 1, etc. So this becomes 50 over 1 plus d to the 2 until 50 over 1 plus d number of cycle. So that's how we are calculating the inflation. In R, we just use the 0 column number of cycle and use the exponential operation. So very simple in R. And we want to calculate the ICER. So what is ICER is the incremental cost effectiveness ratio. So what does ICR mean? So for example, you have 4 strategies. Of course, strategy AB, it is the most expensive strategy. Of course, the effectiveness of AB, will be very high because they're very expensive, then they will be the highest. But is it very most cost effective? That's thing that we want to decide, because for example, you have the budget from the company. You want to get the strategy with the most cost effective strategy. That's why we need to take into account the ICER. In this case, we use the calculate_ICER as function from the DEMPAC library in R. So how we are going to use the function is, first we need to create a factor of all those 4 strategies. So we want to compute the cost and the quality of life, because we want to find the effective and also the cost. That's why we take into account the cost, effect, and also the strategies here. And finally, we get the result. So as you see, the standard of care, as we all, of course, expect the result, standard of care is the cheapest strategy. So it will have the lowest effectiveness, but it will also be the cheapest. So that's expected. And it turns out, this is the thing that will be interested. It turns out that the strategy B, it is the most effective strategy, because you see the strategy A there, it has the lower effectiveness, but it has higher cost. That's why we said that as dominated strategy. So dominated strategy, it means if you already take some economy course, it means the strategy that has at least there is one strategy with higher return on investment. So because there is strategy B, which has higher cost effective, so we call it strategy A as the worst strategy or the dominated strategy. And we have the strategy AB if you have higher cost, but of course you want higher effectiveness. And we can also calculate the probability sensitivity analysis. So we need to know the for example, we have something called NMB. So NMB is the net monetary benefit. So you can calculate the NMB by using the WTP, so the willingness to pay, multiplied by quality adjusted life years. That's how we define the net monetary benefit. And as we've seen in the graph here, if you are willingness to pay less than 80,000, then the best strategy for you is the standard of care. But if you are willingness to pay, if you are willing to pay between 80K to 120K, then the most effective strategy for you is strategy B. But if you are willing to pay more than 120K, it implies you can use strategy of AB. That's why the net monetary benefit will be depends on the willingness to pay and the quality adjusted life year. So from 0 NMB 80K, the highest NMB, so highest NMB means the highest net monetary benefit. So the strategy that you are going to choose will be the highest, will be the strategy with the highest NMB is, NMB highest is strategy standard of care. And if it is between 0K and 120K, strategy with the highest net monetary benefit will be strategy B. If you are willing to pay more than 120K, the strategy with the highest NMB will be strategy AB. And that's how we decide the strategy, the best strategy for our company. And this is the reference for the paper. Thank you for all amazing authors that already created the paper. And thank you for you guys for your attention and for coming to this presentation.